All right, so last time we made that little flip book and we talked about piecewise functions. We practiced graphing them. We're going to do more with that today because I know that's like a tough thing. We'll practice it. And we also talked about continuous versus discontinuous. And discontinuous was just that, the two pieces of the function don't meet up. Today, we're going to classify the discontinuities. So I'm going to, tell you what each of them are called, and then we'll draw a little picture of each. So types of discontinuities. The first is called removable. A removable discontinuity means you just removed a point. So like you could fix it if you could just like put that point right back in. Do you see what I'm saying? It's like you just plucked a point out. So that would look either like just a hole, or sometimes you can have a graph that has a hole in it and then that point is like floating somewhere else. So either just a hole like it's missing, or a hole like, nah, I fooled you, point's over here now, like we stole it, like one of those. But you could fix it and make the graph continuous again if you could just put that point back. It was just like removed. Does this make sense? You just removed a point. All right, and then there's non-removable, which is a more deep-seated issue. You can't fix the graph just by putting a point back in it. So that would be either an asymptote. You can't fix that discontinuity just by sticking a point back in the graph. You're not going to be able to make those two pieces meet up with each other. So an asymptote, or what's called a jump discontinuity, which would be something like that. You can't fix that just by putting a point back in. You did more than just remove a point, like the graph actually is broken. So whenever we do these, we're going to state whether they're removable or non-removable. And it makes sense. This means something was removed. This is, a bigger issue. And we're also going to state the domain and range just to, practice that and be thorough. I'm also going to have you evaluate a couple of numbers just for us to practice doing that again. I'm just making them up. I'm just making up a few examples for us to practice. Let's just do this off to the side here. Let's do f of 2. All you have to do is make a decision. I know that's difficult sometimes to make decisions. Make a decision which piece you're going to plug into, the first one or the second one. So what do you guys think? The first one or the second one? Good. The first is correct. Why the first? Because you're right. Why would 2 get plugged into the first one? Yeah, that's where 2 lives. That's where it's equal to. All right, so let's plug in 2. 2 squared. Or no, I'm trying to wake you up here. 2 squared is 4, but we're going to make it negative. So negative 4 plus 6 is 2. Good. All right, let's try another one. Let's try f of 6. Which piece of the function is 6 going to get plugged into? Where does 6 live? Good. Second one, because 6 is bigger than 2 last time I checked. So if you plug 6 in there, half of 6 is 3. Let's try one more. Let's do f of 1. Where is 1 going to get plugged in? The first one, because 1 is smaller than 2. All right, so if you plug in 1, 1 squared is 1, make it negative. Negative 1 plus 6 would be 5. So, that's just how you evaluate. Just make a decision which piece you're going to plug into. All right, so graphing this first piece, I would start at 2 and then just plug in some numbers smaller. It's going to look like an upside down parabola moved up 6. So actually, you can go ahead and put a point up 6 if you want to. 1, 2, 3, 4, 5, 6. And the graph is going to be an upside down parabola. But it's going to get broken or cut. Do you remember we took our scissors and actually physically cut the flip book? It's going to get cut at 2. Now we already plugged in 2. We got 2. So we can plot 2, 2. Open or closed circle, do you think? It's going to be closed because of the equal to. Good. So 2, 2 will be a closed circle. And then you'd want to plug in some numbers smaller than 2. We already plugged in 1. I had you practice a few of these. We plugged in 1, we got 5. So you can plot 1, 5. And then, work smarter, not harder. Because it's a parabola, it's going to be symmetric. And so you can get the symmetric points on the other side. You can, of course, make a table and plug in as many points as your heart desires. But if you know it's going to be symmetric, that saves you some time. I'm not telling you to be lazy. I'm telling you to be efficient. And then when you connect it, you just don't get the whole graph. You only get from 2 and then numbers smaller than that. So it's a parabola that got amputated. It just got cut off. Some people like to graph the whole thing and then just erase the part they don't want. If you're like that, you can do that. Right? All right, and then here we have 1/2 x. That's going to be a line with a slope of a half. We just only want it from 2 onwards. But Ms. Cole, you can't plug in 2. Do you remember we had this conversation? You can plug in 2. It's just, what do you have to put? Open circle. But you can plug in 2. If you plug in 2, what do you get? Yeah, half of 2 is 1. Good. So you're going to get 2, 1, be an open circle. And then you can do your slope of a half, up 1 over 2. And it's going to look like a clock hand. Anytime you have something linear, it looks like a clock hand. So is this graph continuous or discontinuous? Discontinuous, good. And we're going to state removable or non-removable. So could you fix it just by putting a point back in? Like if I just stuck a point back in the graph, could I make it connect again? No, there's an actual jump. That's a jump discontinuity. So it is non-removable. So we have a non-removable discontinuity. You can abbreviate that disc. Non-removable discontinuity. And then you want to state where. At x equals where? Where does that happen? 2. So non-removable discontinuity at x equals 2. And then I said, let's do the domain and range just for the sake of being thorough here. You can just put D for domain, R for range. Domain, we're going to sweep left to right. I know this arrow is pointing down, but it's going to keep going to the left forever. This goes to the right forever. And this piece picks up where that one left off. So we didn't lose anything. Your domain is all real numbers, negative infinity, positive. And then for range, you're sweeping downwards to upwards. Well, this side goes down forever. And as you sweep upwards, look, we're not missing anything. I know that there's a hole there, but we still get that point right here. This part picks it up. And then this arrow is going to go up forever. So again, we didn't lose anything. I just always like take my pencil and it's like scanning, scanning, scanning. And as long as you don't lose any numbers, then you've got it all. All right, let's try another one. First piece, it's just 4. What's that going to look like since it's just a number? Good, constant. It's going to be a flat line at 4, so like this. But we only want it for numbers smaller than -3. And do we want an open or closed circle there? Good, closed. All right, so you're going to have a flat line at 4, so like this. But it's going to get cut off at -3, like a little clock hand. Again, some people like to draw in the whole thing and then just erase the part they don't want. If you want to do that, that's like totally valid. Just make sure you put in a closed circle then. All right, and then this one's absolute value, so it's going to be a V shape. How did it get shifted? Good, right 1, so V shape that's right 1. We just only want it to be between -3 and 2. All right, so here's what I would do. I would shift it right 1. That's going to be the center point of your V. And then I would plug in these endpoints, -3 and +2. Ms. Cole, you can't plug in -3. Yes, you can. It just needs to be open circle. All right, so let's plug in -3. -3 minus 1. -4, absolute value that 4. All right, so we get -3, 4. Hey, look. It's this point right here. That means that the two parts connect right there. You can't put an open circle on top of a closed circle. It just means that they connect. And then I would plug in 2. 2 minus 1 is 1. Absolute value, that is 1. So you get 2, 1. So again, it's a V shape, but you just didn't get the whole thing. We chopped it off from -3 to 2. You're only getting a piece of it. And then square root, but we only want it from 2 onwards. So I would plug in 2. You can plug in 2, you just need to put an open circle, all right? If you plug in 2, 2 times 2, 4, square root of 4, 2. So you get the point 2, 2, just make it open. And I'd like to get at least one more point. It's going to go off to the side like this. But let's try and find one more number to plug in. What's another number we can plug in? You want to be careful. Pick something so that you can actually square root whatever we get. What'd you say? Now, if we do 4, 4 times 2 is 8. I can't square root 8 without a calculator. Let's try 8. 8 times 2, 16. Square root of 16, 4. Good. So 8, 4. If you pick a number that doesn't work, just pick another number. It is so not a big deal. All right, continuous or discontinuous? All right, discontinuous, removable or non-removable? Non-removable. You can't fix it just by putting a point back in. So non-removable discontinuity, you can abbreviate that, at x equals, where did the break happen? 2. Then we'll do domain and range. So what do you think for domain? Scanning as I scan left to right here. What do you think? Yeah, you get everything. This piece picks up where that one left off. So you didn't lose out on anything. It's all reals. Range is not going to be all reals. All right, look, scanning. What y value do we start at? Get 0 with a bracket because there's actually a point. And then as we keep scanning upwards, and I know this is tricky, this looks like this is just flattening out here. It's because it got, what would that be? Horizontal shrink, it's because of the dilation. But this arrow is going to keep going upwards forever. It's not in a great big hurry. It's sort of lazy, but it is going to keep going up forever. So it will be, like onwards. I know it doesn't look like it, but it'll keep going forever. Infinity is not something we can actually grasp as a concept. You know what I mean? Like, just don't try too hard. All right, we'll do this one, then we'll do another little brain break. All right, 2 to the x. What type of function is that? All right, yes, swoop, exponential. We only want it for numbers up until 1. So I would plug in 1, and we're going to just need an open circle. So if you plug in 1, 2 to the 1, 2, all right? So you get 1, 2, just make it an open circle. And then let's plug in some numbers smaller than 1, like 0. Let's try 0. 2 to the 0. 1, good. So 0, 1. And that's good enough. You're going to have this asymptote here because it didn't get shifted. It'll still be on the axis. And then something like that. It's a swoop, but we only got part of it. It got chopped off there at 1. Let me darken this up. I'm sorry, the printer was not printing very dark the day that I ran these copies. All right, and then this one's going to be linear. Oh, I should have asked you that. What shape is this one going to be, guys? Linear, slope of -1. You just only want it from 1 onwards. So again, let's plug in 1. We'll just need an open circle. So if you plug in 1, -1 plus 3 be 2. So this is going to connect. But does the circle get filled in? No, 1 is actually not a part of this graph. You don't have an equal to on there. So it's going to start at this point, and then we're going to do our slope of -1. So down 1. So it'll do something like that. 1 got kicked out. 1 is not invited to the domain party. Poor 1. 1 got left out. And we'll write that in a second when we do the domain. But first, continuous or discontinuous? Discontinuous, removable or non-removable? This one's removable. You could fix it if you could put that point back. So removable discontinuity at x equals 1. And then domain and range. So we just kind of talked about domain. Scanning left to right, you get everything except 1. How do we kick 1 out of the domain party? Because 1 is a problem. Do you remember how we write that? Good. Negative infinity to 1, union 1 to infinity. It's saying we want everything to the left of 1, everything to the right of 1, but not 1. All right, and then range, scanning downwards to upwards. Well, we get everything down here up until what y value? Good, 2. So we want negative infinity to 2, and will 2 get a bracket or a parenthesis? Yeah, good. Why a parenthesis? It's not there. It's a hole. It's not included. All right, do a little brain break. I'm going to pause the recording and then we'll do the stuff on the back. All right, so looking at this one on the back, it says f of x equals x. All right, so that's just this line through the origin, slope of 1. We want that everywhere except for x is 3. It's like the no parking sign, like the not equal to. So you want that line everywhere except at 3. So this is a case where I would just draw the whole thing and then erase it at 3, because you want it everywhere except at that 1 point. So for y equals x, you're going to go through the origin, slope of 1, and draw that in, and I'll wait till everybody draws that, and then we'll just erase the part we don't want. Because in this case, there's only 1 point where we don't want that, which is 3. So just watch me take my eraser and do this. All right, here's 3. Find out on the graph, it's 3 because it's y equals x. So it's the point 3, 3. We're just going to pluck that out of the graph. We removed it as foreshadowing for what type of discontinuity this is going to be. We just removed that, but it's like we stole it. We kidnapped 3. And where did we put it? Well, when x equals 3, where do we want that point to be? At -2. So at 3, -2, you have that floating point. We stole 3 and we stuck it somewhere else, is what happened. What's that? It's brutal. All right, so this is a removable discontinuity at x equals 3. So it's like that little floating point. Nah, I fooled you. Point's over here now. So domain and range. For domain, when you scan left to right, you still get everything. There's still a point when x equals 3. It's just down here instead of up there. So you still get everything. Domain is still going to be all real. Range is not, though. There's one number not invited to the range party. As you scan downwards to upwards, who got left out? What y value here? 3. 3 has that hole at it. So we want everybody except 3. 3 got left out. 3 is not invited to the range party. Now for these ones, we're going to do that backwards. You have the graph, we're going to try to write the equation. Again, just for letter A, let me make up a couple values for us to evaluate. This is just practice. I'm just making them up. Let's do f of 0. What that's asking is you want the point 0, comma, whatever. So just find that on the graph. It would be 0, comma, what? Not 5, but -5. There we go. You may have said negative. I just didn't hear you. I'm sorry. And let's try where the break happens. Let's do f of -1. When you want the actual point, you want the filled in circle. So f of -1 would give us what? Yeah, -5.5. Let's just call it -5.5. And let's do f of -3. I'm just making up a few for us to try. It's not hard, but I just want you to know how to do it. F of -3. 0. All right, so that's all you've got to do is find the point. Now I left some space here for us to write the answers. So let's go ahead and just write letter A. You're going to have f of x equals, and then one of those swirly brackets. Because Cole, I can't draw that. Just draw a squiggle then. I don't care. I'm not grading your art skills. It's fine. many pieces was this broken into? 2. All right, so we're going to have the parabola and then the domain for that, and then the line and then the domain for that. So this is a parabola. 2 things have been done to it. What are the transformations that have been done to this parabola? Left 3, good, and then it's reflected. All right, so we're going to need a negative out front, and to go left 3 would be x plus 3. You still need something else. What else do I need in there? Good, squared. Perfect. That's it. You're just writing that equation. Now next to it, like right here, you want to put the domain. So we want that graph for everything less than what x value? -1. Good. So it'll be x less than -1. Why not an equal to? Why did I just do less than? It's an open circle. All right, and then we're going to do this equation. It's a line, so we're going to do y equals mx plus b. It looks like the slope is up 1/2. So slope is a half. It'll be 1/2 x, and then our y-intercept is -5, or you could think of it as like it went down 5. So 1/2 x minus 5. And then what's the domain for that piece? What will I put over here? X is what? Good. Greater than or equal to -1. Perfect. All right, let's try letter B. This one's in 3 pieces. So draw yourself an f of x equals swirly bracket. All right, the first piece. What type of function is that? Absolute value. It looks like it went left 4, down 1. Because that's where our center point is. So to go left 4, it'll be x plus 4, and then -1 for the down. And so what do I want to write off to the side here for that domain? I only want to graph it for number what? -2, so it'll be x is perfect, less than or equal to -2. All right, now the second piece is just a constant function, so there's not much to that. What are we going to put for that? It'll just be a number, right? Yeah, good. Literally just the number -2. That's all that is. And we want that from -2 until +3. Now, your little alligators are going to eat left to right. Now they want to eat the bigger number. All right, just make them go left to right. We want to go from -2 to +3. -2 is an open circle, 3 is a closed circle, so just be careful with those symbols. But if, like, people are always like, I'm scared I'm going to get it backwards. Just make your little guys, your little alligators, eat left to right, and then you'll be good. Or think of it as like Pac-Man. I don't know, whatever. They just go left to right. All right, and then this last piece, this is linear. It looks like our slope is -1, down 1/1. So it's going to be -x, and then I need the y-intercept. Here's where this is a little tricky because I can't see where that graph touches the y-axis. So here's what you want to do is just kind of like in your mind, trace this over to see where it's eventually going to hit. So where is this, if you go, up 1/1, where is this eventually going to hit the y-axis? At 3, good, so +3. So you kind of have to do that mentally to see where it's going to touch. So -x plus 3, and then domain for that one, we'll put x is what? Good, x is greater than 3. And then letter C. F of x equals swirly bracket. Thank you. So this is a constant function. We're just going to put -2, and we want -2 everywhere except what x value? -1. So you can just say x not equal to -1. It's like the no parking thing. We want that graph everywhere except -1. And then when x does equal -1, where do you want the point? The kidnapped point, where did we take it and put it? Yeah, at +2. All right, so that's doing what we just did backwards. You have the graph, you write the equation. Did that go okay? We're doing that. People probably like this better because you don't have to actually do a graph. All right, and then these last ones. Find A so that the graph will be continuous. All right, if the graph is continuous, that means the two pieces meet up. Are you following me there? You just want them to meet and make friends. That means you're going to set them equal to each other. It is literally that simple. You're going to take this 5x squared plus A, and set it equal to the 3x. If you want the two pieces to meet up, set them equal. That's logical, right? Like that makes sense. And then you're going to plug in the cut value for x. You have to plug in something for x. So what do you think we would plug in for x for this one? Yeah, -3. So everywhere there's an x, you're going to put a -3, give it a hug, and then we'll solve it. It's like an algebra 1 style equation. We're just going to work it out and solve for x. So set them equal, plug in whatever your x value is, and then solve it. All right, -3 squared. Good, +9 times 5, 45. Good, 45 plus A equals -9. My son is doing the times tables right now in 4th grade, flashcards. All right, and then you're going to subtract over the 45. So A would be -54. All right, and then same thing here. Again, if you want it to be continuous, you just want the two pieces to meet up. So you're going to take that 2A squared plus x equals 3x plus 7A. You're just setting them equal. And then what do we plug in for x this time? 2. Plug in 2 everywhere that there's an x. I made this one more like an algebra 2 style problem to solve. This one's going to be a little bit more grown up. All right, so we'll have 2A squared plus 2 equals, this would be 6 plus 7A. Whenever you have a squared, whenever it is a quadratic, I call this evacuate. Evacuate, evacuate. Get everybody out to one side so that it'll all equal 0. We're going to shift all of this over here so that it all equals 0. So we would subtract the 6 and we would subtract the 7A. You want to put it in order. So it's 2A squared minus 7A, and then 2 minus 6 would be -4. I'm obviously going to tell you because I'm your teacher and I'm going to give you the answer. But does anyone remember what you did next? Because you did do this in algebra 2. Once you got it all equals 0, what did you do with this? Factor. Good. We're going to factor. This is like your little review of factoring. FYI, for pre-calc, we don't reteach factoring. It's kind of like it's an assumed skill coming into pre-calc, and I'll kind of review it as we go through problems like this, but I'm like just letting you know about that, right? So numbers that multiply together to be 2 would be 2 and 1. We'll have 2A and 1A. And then how would you want to split the 4? You could do 2 times 2, or you could do 1 times 4. It's going to need to be the 1 times 4. And I will point to it. You want the outsides. Remember when we did FOIL and the outsides and the insides? This is FOIL in reverse, all right? We're trying to split it apart. You want the outsides and the insides to give you a -7. If we multiply the outsides, what are we getting? 8. 2 times 4 is 8. This guy? Okay, 2 times 4 is 8. And then the insides, just 1. So if you do -8 plus 1, you will get -7. You're trying to balance that to get what gives you in the middle. And then I apologize, I ran out of space, so I have to write the answers over here. You get 2 answers, 1 for each factor. You're setting each of those equal to 0. If you set 2A plus 1 equal to 0, what would that give you? If this equals 0, what is A going to have to be? Not a half, but -1/2. Good. And if you set this factor, A minus 4 equal to 0, what will you get? 4. So 2 answers for that one.